Good day, friends. The topic that unites us today is the universe. We will talk about the history from the birth of space to the formation of planet Earth. I think it is important to answer the key question right away. Why is the history of the universe important? As fascinating as it is far from our everyday life. You don't need to know about the Big Bang to pay off a loan. Knowledge of huge cosmic structures won't help you do a renovation, and understanding quantum physics won't help you buy a car. Deep exploration of space gives us something different. This is an opportunity to learn and realize the insignificance of our problems and forgetfulness compared to the scale of the universe. This is truly a chance to take a new look at our world and our lives. When we study the history of space, we see how it has changed over billions of years. Before our eyes, the universe is evolving from a small point to huge structures. And most importantly, intelligent life has emerged amidst the chaos of physical processes on our small planet. The universe is aware of itself through us, through the consciousness of people, and thus we understand our involvement. Our life is of great importance. We have our own role in this huge cosmic spectacle. History is truly one of the most fascinating and at the same time difficult subjects to study. Knowledge of history plays an important role in understanding one's place in the world and in the universe. But where to start studying history? Traditionally, the study of history begins with the appearance of the first written sources. This moment is usually called the beginning of historical science. The events of the past of mankind, the creation of states, wars, the development of culture, etc., are described. However, this approach does not give a complete picture of the conditions in which humanity evolved. Where did society come from? Where did life come from? How did we come into existence as a species? To answer these questions, we need to turn to a science called paleontology. It helps us understand how life on Earth arose and evolved, but it does not help us see the whole picture. What space is the Earth in? How did it form and where is it? To really answer all the questions and see the whole picture, it is important to start at the beginning, with the Big Bang. First of all, let me start with the bad news. Humanity actually knows very little about what happened at the beginning of cosmic history. Also, our view of the modern universe is limited to a small part of it. At the beginning of time, our tools for studying it practically stop working. The laws of nature that apply in modern times become meaningless there. To understand what happened then, we need new theories and a fundamentally new understanding of physics. At the moment, many questions remain unanswered. Were there other universes before ours? Or is our universe the first and only one? What caused the Big Bang? Perhaps it happened on its own, according to laws that we do not yet understand. Or was there something before the universe? We do not know the answer to these and many other questions. And perhaps we will never know. But this is no reason to despair. We will use what is currently available to us and form our own model of the cosmos. The starting point of our journey is the singularity. This is the supposed state of the universe at the initial moment of the Big Bang. For the first fraction of a second of the universe's existence, it was concentrated in one point. This phenomenon can be thought of as the concentration of an infinitely large mass in an infinitely small volume. It is known for certain that there is a certain moment in time at which the universe was born from a singularity. But we cannot obtain any knowledge of what was before the singularity from calculations or observations. And most importantly, we do not understand how the cosmological singularity gave birth to the unimaginable reserves of matter and energy of our universe. We call a singularity what we cannot understand. What led the singularity to the Big Bang? Having undertaken to reveal the main secret of the universe, researchers received not one, but quite a few answers. Most often very strange, complex, and unprovable at the moment. The main answer was that before the Big Bang, there was nothing at all. It turns out that nothing gave birth to everything. It is extremely difficult to imagine that the universe could have arisen from nothing. However, scientists insist on their own. They say that they did not just come up with the idea that the universe arose from nothing, but came to this conclusion as a result of strict mathematical calculations, in which no one has yet found an error. But what is absolute emptiness? Perhaps nothing is not only the absence of matter, but also the absence of space and time itself. Try to imagine, in absolute silence, not a rustle, not a sound is heard. There are no sensations except complete absence. There is no light, no darkness. Everything is immersed in absolute nothingness. In this emptiness, there is nothing but infinity. There is not a single landmark, not a single point. There is nowhere to look. Everything is filled with nothing but emptiness. But there is another idea. Nothing had the usual forms of matter, but it was not completely empty. There were some processes that led to the appearance of our universe. To find confirmation of this hypothesis, researchers are trying to create something similar to nothing. They try to do this in an experimental setting. Special chambers are built from which particles of matter are removed, and the temperature is lowered to the cold of outer space. But no miracle happens. The resulting nothing is actually something. It can be studied in many ways, and yet many do not agree that the universe arose from nothing. The key idea is that the Big Bang is an outstanding event in the history of the universe, but not the original one. There is no idea what this pre-existence of our universe was like. But something happened in its history that led to the Big Bang, which created our universe. According to another view, the universe has existed forever, and in its history Big Bangs are followed by Big Bangs. Such explosions could occur if the expansion of the universe was accompanied by its contraction. The infinite loop solves the problem with emptiness, but creates the problem with infinity. It is indeed difficult to imagine and describe this endless huge mechanism, but it had to start somewhere. And in what space is it located? This theory also does not give a complete answer to all the questions we ask. And the questions of singularity are difficult in themselves. In science, explanation is based on cause and effect. But if nothing is actually an absolute void, it has no chance of becoming a cause. It is not that we cannot find the right explanation. It is just that in the face of nothing, explanation does not work. And this refusal hits a sore spot. We are creatures that love narratives. Our simplest concepts are carried out through stories. And how something came to be here, nothing, is the most important story. A plot more fundamental than the hero's journey or boy meets girl, but this plot itself undermines the essence of the story. This is a hangman of self-destruction and a paradoxer. Its main character is nothing. The word is paradoxical due to its very existence as a word. As soon as we imagine it or name it, we destroy its emptiness and stain it with meaning. And the question arises, is this a problem with nothing? Or is it our problem? A cosmic problem? Or linguistic? Ideological? Or psychological? A paradox of physics? Or thoughts? It is difficult for us to imagine that before the beginning of our history, there was nothing. Our psyche, our nature does not allow us to believe in it fully. We try to prolong history, to find a new beginning, postponing the meeting with emptiness. Nevertheless, there is an edge to the history we know. Something happens. A turning point occurs. History is launched. History begins to exist at the smallest point. The chronology of the universe is launched. The Big Bang occurs. Different people understand completely different things by the word universe. For example, the concept of everything exists, but it would be necessary to narrow the concept and define it to something specific. Most cosmologists would probably agree that the universe is a space completely contained, in which we are, and which can theoretically be covered by a continuous, smooth, coordinate grid. The universe, as a philosophical idea, has a meaning close to the concept of the universe. The universe is a concept that denotes all of reality, with its inherent attributes, time and space. We are now studying this reality from the point of view of ordinary physics. Time and space begin in the Planck era. It is separated from the Big Bang by intervals of only a few trillionths of a second. Why this interval? Why do we count history from this moment? Why not earlier or later? In short, and very conditionally, we are talking about the indicator at which all existing theories stop working. That is, we will not be able to measure a distance smaller than the Planck length simply because the laws of physics limit us. This is the limit for us. The Planck time is also called the quantum of time. That is, the smallest value of time that has any actual meaning. And at this moment, the universe occupies a space the size of the Planck. Think of the smallest thing you can imagine: bacteria, viruses, atoms. The Planck length is so small that if an atom were the size of the Earth, the Planck length would be much smaller than the head of a pin. During the Planck era, the entire observable universe was concentrated in a region many trillions of times smaller than a proton. And general relativity, our usual physics, simply does not help us in describing this time. The physics of extremely small particles, i.e. small in energy portions, comes into play. This physics is governed by quantum mechanics. During this period, the universe appears to consist of a gathering and dynamic quantum foam. This foam arises from the dynamic and unpredictable nature of interactions at the quantum level, i.e. at the level of smaller parts. At very small distances, space is considered to have a rough, flat structure, trembles chaotically, constantly changes shape, and has a spongy and foamy structure. For example, in this curved space, light travels a different distance between 2 points than in classical space. Since the curvature of space along the ray path changes over time, the speed of light between 2 points will fluctuate chaotically around some average value. Quantum micro-black holes spontaneously appear and then disappear without a trace for no apparent reason. The universe at that time had the highest possible temperature and energy. In this high-energy, ultra-compact space, with the slightest push, anything is possible. On small scales, where the smallest clumps of energy and matter exist, a completely different set of rules applies. In this space, nothing is ever where you expect it to be. The very act of observation changes the outcome. Instead of dealing with constant absolutes, quantum physics considers probabilities. Nothing stays the same there for long. In this world, processes occur that boggle the imagination. The largest particles behave completely unpredictably. They disappear and reappear out of nowhere, interacting with each other. They do this at incredible distances, violating all our possible explanations. The impulses that drive these particles defy classical physics. Anything is possible here. For example, 2 or more particles can suddenly behave as if they were one, even though they are separated by space and time. Particles can instantly transmit information to each other, violating the laws of relativity. This lawless quantum world reigns only at nanoscopic scales. As we reach more familiar scales, the dominance of probability in the laws of physics diminishes. But in the Planck era, the entire universe was quantum. This is the problem of understanding how things actually worked at that time. General relativity and quantum mechanics are fundamentally incompatible with each other. So researchers are still searching for a solution, the so-called theory of everything, which can reconcile the two most important theories of modern physics. If it is created, it will be able to describe how the universe would have behaved in the Planck era. During this era, the universe was like a seething cauldron, where space and time were intertwined, matter and energy were inextricably linked. Everything was turbulent. There was chaos. Nothing could be constant or stable. At the same time, the universe was extremely small and so dense that even the smallest particle of matter contained an enormous amount of energy. After a tiny amount of time, the Planck era, characterized by its unpredictability, ends. The gradual increase in size and cooling of the universe signals us the transition to a new era. All the energy of our cosmos is still compressed into a tiny space. This period is characterized by colossal temperatures of many trillions of degrees. The universe gradually grows and also gradually cools down. I repeat, what exactly happened during the Planck era is not very clear to us. We can imagine that, most likely, it was very similar to the quantum world with its random fluctuations. But unfortunately, we cannot paint an accurate, reliable picture of that universe. We are simply moving on to the next era, the era of great unification. At the beginning of time, when the universe was hot and had unimaginable properties, the fundamental forces of nature were inextricably linked with each other. In this primordial mixture, there was no separation into separate elements, and each particle had the properties of all the forces. But over time, the universe cooled down, and the first fundamental changes began to occur. From some kind of energy soup, the force of gravity emerges. To fully understand the picture, we will have to jump forward 13.8 billion years. The present, what forces in our current universe do we know? I think you know gravity, the tension in a string, the compression of a vein, and maybe some other examples. But all of these forces are derivatives of the four fundamental forces that are responsible for everything in the universe: gravity, the weak force, electromagnetism, and the strong force. What are they responsible for? Let's start at the beginning. Everything around us is made up of particles. The fact that the Earth is round and the sky is blue is due to the way different elementary particles with different properties interact with each other. Elementary particles are the primordial, indecomposable building blocks of all matter. Elementary particles are endowed with fundamental forces. Before we continue, it is important to understand particles have properties or something inherent to them that allow them to respond to certain types of forces. Such particles are called fermions. They are quarks of a lepton. We will get to know them in the future. Other particles carry these forces and interact with the former. This is the basin. All processes in the universe arise as a result of these interactions. For example, the weak interaction is the basin, which is responsible for changing the type of fermion. Changing the type of fermion entails a change in the entire chemical element, which leads to decays and chemical processes. Our complex world could not exist with constant decay. What gives the world its structure? The short answer is the strong interaction. We exist thanks to atoms. Atoms exist because of their nuclei. Nuclei exist because of particles. Strong interaction. They do not decay, unlike particles with a weak interaction. We are completely made of atoms that are glued together by the strong interaction, and we cannot ignore other fundamental interactions: electromagnetic and gravitational. Electromagnetic occurs in the presence of electric charges, and magnetic when they move. A changing electric field generates a changing magnetic field. The carrier of electromagnetic interaction is uncharged matter. That is, the basis of the electromagnetic field. This type of interaction is typical for electrically charged particles. Since atoms consist of oppositely charged particles, electromagnetic interaction plays a key role in modern physics. Gravitational interaction is the weakest, and therefore is not taken into account in the theory of elementary particles, which is what we will mainly talk about with you. At characteristic small distances, the influence of gravity is insignificant. In general, gravity plays a decisive role on a cosmic scale. So, we have analyzed the 4 fundamental villages. If we sharply and significantly increase the temperature, then the individual properties of the weak nuclear interaction, the electromagnetic interaction, will begin to weaken and merge with each other. We will no longer see individual parts of electromagnetism and parts of the weak interaction, but rather a combined impersonal force of 2 combined interactions, the so-called electroweak village. As the energy increases, the same concept applies to the strong interaction and already to the chimeric electroweak. At high enough temperatures, they also merge into a single whole, a procession that we know as the grand unification. This final unification of the 3 basic fundamental forces gives rise to the electro-strong interaction. There is a good analogy for understanding this unification. It does not convey all the subtleties very conditionally, but for our purposes it is more than enough. Imagine a coin with a minus on one side, for example, 1 ruble, and an eagle on the other side. We need to choose one of the sides by flipping the coin. The decision is made only when the energy from the coin toss runs out, and the coin no longer shows one side. Up until that point, while the coin is still filled with energy and spinning in the air or on the table, it is virtually impossible to distinguish between its 2 sides. We have 2 choices. There is only one spinning ball with its own characteristics. This is what we are faced with when we study the behavior of the fundamental forces. At the high energies that were present in the nascent universe, this single ball consisted of 3 forces. And will gravity, the 4th fundamental force, ever be accepted as a single whole? According to our data, in the Planck era, all 4 fundamental forces were a single whole. And as we remember, very, very little is known about the Planck era. A complete study still requires a theory of everything, that is, a unification of relativity and quantum mechanics. It is still completely unclear to us what would happen if all 4 fundamental forces became one. But for now, it is time to return to the starting point. We will proceed in the reverse order of what we described earlier. The temperature of the universe gradually drops. Gravity separates from the 3 merging fundamental forces, and we find ourselves in the era of grand unification. The tiny space is filled with particles. Photons spontaneously turn into matter, creating quarks and leptons. These nascent particles are extremely short-lived and quickly decay back into photons, barely having time to form. Electro-strong bosons only complicate the picture, helping quarks turn into leptons, lepton into quark, matter into antimatter, and vice versa. The interactions create a complete mess. The temperature drops by a factor of hundreds. The tiny universe becomes slightly colder. This shift will allow the strong interaction to break free, and this will lead to a new shock for the young cosmos. At the very beginning of this ISS, I said that our history begins with the Big Bang. I've been telling you about the processes that take place in the early universe for quite some time now. We have already passed 2 epochs, but there is no mention of a global explosion anywhere. We are talking about quantum processes that take place in a tiny universe in very short periods of time. The rapid growth that will turn into a smooth expansion began precisely at this stage, the inflationary era. It is this extremely rapid expansion that is called the Big Bang. And now we will take a closer look at how this happened. With the energy drop and cooling that led to the end of the Great Unification, a phase transition occurs. The strong and nuclear interactions are released. During this phase transition, a scalar field known as the inflating field is theoretically formed. This hypothetical field is supposed to fill all of space and at any given time takes on different values in arbitrary spatial regions. Like all fields, the inflating field has a certain intensity at every point in space-time. This intensity determines how the inflating interacts with other fields. During the inflationary expansion phase, the inflating field intensity is almost constant everywhere. Depending on the strength of this field, it has a certain amount of potential energy. It is the potential energy of the inflating field that is a possible cause of the accelerated expansion of our universe. Over time, this energy decreases, but at the moment of inflation, the rarefaction of the scalar field is responsible for the creation of a vacuum, that is, space-time. Changing the inflating potential is like inflating a balloon, only instead of air there is a vacuum, and instead of a balloon there is our universe. Okay, I think that was extremely difficult. This interaction is almost impossible to describe in simple words. It is very difficult to imagine it outside of formulas and deep theories. It is important for us to understand, to generalize, some almost magical theoretical field due to complex physical processes made our universe expand at an incredibly high speed. In a split second, the universe with all its fluctuations, chaos, and strange processes stretched from the size of a speck of dust, which is smaller than it, to a universe the size of a fruit. And this happened faster than the speed of light. It would seem that physicists say that it is impossible to move faster than the speed of light. But the speed limit affects the processes inside the universe. But no one forbids the universe itself to be faster. This rapid expansion is that very explosion. Before inflation, the universe experienced chaotic fluctuations, random, unpredictable movement, similar to the movement of dough in a mixer. That same foam we talked about earlier. After a sharp increase, the heterogeneity of the quantum scale instantly increased to a large-scale structure. Quantum fluctuations became areas of superdensity, which served as the basis for the huge structures of the modern universe. This expansion, fast and furious, inevitably cooled and emptied the cosmos. The expansion of space means that the elementary particles that remained after the grand unification era are now spread throughout the universe and have acquired a very low density. However, at the end of the inflationary epoch, a huge energy was released from the inflating field, and it filled the universe again with a dense, hot mixture of quarks, gluons, and thus transferred the universe to the electroweak epoch, which is the next part of the first second. Yes, it is very important to note at this stage that we are still very far away, even at the end of the first second of the universe. So rich is the life of our still barely formed universe. There are quarks, electrons, matter, and antimatter. All of them are controlled by gravity, the strong nuclear force, and the chimeric electroweak force. But the temperature and energy are still too high. The strong force that holds the particles together cannot yet have any real effect on the particles. Tiny particles of energy cannot combine into anything coherent and new. Gravity also has no effect on the overloaded particles in this post-inflationary maelstrom. One key ingredient is missing, making gravity essentially powerless at this point, unless the newly formed particles are given mass rather than left unchecked. Another energy dump and another cosmological transformation will be required. And only then will we reach a universe that shows the distinctive features of our modern universe. The universe at the beginning of the Big Bang was tiny, hot, and formless. It was the point where time and space merged to create an unimaginable force. Everything was compressed to its limit. Its shape was constantly changing, as if it were searching for its place in space and time. It was not round or square. It was more like a blob of fluid energy, pulsating and changing with each passing moment. This strange universe is expanding. It has become many times larger, but the question remains, what exactly is expanding? What material does the universe consist of? In what form? In what state of aggregation is it? To do this, we need to delve into physics. From the school course of this very physics, we know four basic states of aggregation. Substances in a solid state have a fixed volume and shape. The particles are arranged in an ordered structure. Substances in a liquid state have a volume, but do not have a specific shape. They easily change their shape under the influence of external forces. Particles of a substance in a liquid are close to each other, but move freely. Substances in a gaseous state have neither volume nor shape. Gas particles are at a large distance from each other and move very quickly. They occupy the entire volume provided to them. As the temperature increases, the substance becomes less structured. Temperature depends on the speed of movement of the particles, and accordingly, the higher the speed, the hotter. To generalize, the higher the speed, the weaker the bonds between individual molecules. Cold solids gradually melt when heated and become liquids that retain the same volume, but not shape. They, in turn, evaporate when heated, turning into gases. They no longer have any shape or volume. And if you continue to heat the gas, but at the same time use pressure to prevent its particles from flying apart, it will turn into plasma. It is characterized by high temperatures and ionization. That is, an electric charge appears in it. When the gas is heated to high temperatures, its atoms begin to move faster and faster. They accelerate until they begin to overcome the electromagnetic force due to speed. At this point, the electrons are separated from the atom, and the gas becomes composed of charged particles. And if we continue this series, then if we continue to heat the plasma even more and maintain the pressure, we will get quark-gluon plasma. The difference is that in ordinary plasma, due to high temperature and pressure, positive and negative particles move freely. In the form of plasma, a similar process occurs with even smaller particles, quarks. Here it is also important to go deeper. Let's start with a simple question. What are the objects around us made of? Our world, like a house, consists of many small bricks, chemical elements, which, when combined in a special way, create something new. If you look closely at them, you can see that there are not so many different types of blocks. They just connect to each other differently each time. This is how they form new forms and phenomena. This is chemistry. Let's take some substance as an example. Let's say it is the second element of the Mendeleev table, and Ely's nerve gas. Like other substances in the universe, helium consists of molecules, which in turn are formed by bonds between atoms. In this case, helium is a little special for us because it consists of only one atom. What does this atom consist of? A helium atom consists of two neutrons, that is, neutral particles without a sign, and two protons, positively charged particles with a plus sign. They form an atomic nucleus around which two negatively charged electrons revolve. It is important to note that the only thing that is absolutely indivisible here is the electron, which is a negatively charged particle orbiting the nucleus. The neutron protons are part of a group called hadrons, particles that are subject to the strong force. The strong force is what binds hadrons together to form an atom. The nucleus is made up of neutrons and protons due to the very strong attraction that binds them together. What are these parts of the nucleus made of? The neutron, as its name suggests, is neutrally charged and can be split into 2 down quarks and 1 up quark. The proton is a positively charged particle. It is split into 1 down quark and 2 up quarks. Next, I suspect we need to figure out what a quark is. A long time ago, scientists came up with a convenient and concise way of representing elementary particles. It is called the Standard Model. All elementary particles are divided into fermions, which make up all matter, and bosons, which mediate the various types of interactions between fermions. First, what are fermions? Think of them as Lego bricks. They fit together to form the universe. The main rule: don't be where I am. The special thing about fermions is that no 2 fermions can occupy the same place at the same time. This allows them to build everything from atoms to planets. Fermions are divided into quarks and leptons. Quarks combine to form protons and neutrons, which make up the nucleus of an atom. We said earlier that a proton is made up of 1 down quark and 2 up quarks, which are glued together by the strong nuclear force. But this force does not affect the second class of fermions, leptons. Leptons include the familiar electrons that float around the nucleus of an atom. Also in this class are electron-like particles like taus, muons, and neutrinos. Because of the strong force, quarks cannot exist on their own. When we try to separate quarks, their attractive force actually increases. This means that in the modern universe, it is virtually impossible to find a quark that exists on its own. But leptons are particles that can exist on their own, and they can be separated from other particles. Okay, what is a basin? They are the intermediate forces that bind and repel matter. They can also explain why small atoms can collapse into larger ones, and why larger ones sometimes break apart. Basins include photons, which are particles of light that carry the electromagnetic force. Gluons, which carry the strong nuclear force and bind quarks together. W and Z basins, which deal with the weak nuclear force. And together these particles carry the properties of matter. If quarks and leptons make up an atom, then basins make them stick together. You won't be able to remember these structures right away, but for our purposes, you don't need to. At this point, it's important for us to understand the general scheme of the world of elementary particles. Let's go back to the first second of the universe's existence. The electroweak interaction is divided into 2 parts. At very high energies, a number of exotic particles are formed, such as the Higgs boson. The particles acquire mass due to interactions with an invisible electromagnetic field known as the Higgs polyhedron, which carries the particles of the same name that we talked about earlier. Some particles are able to pass through this field without acquiring mass, while others get stuck and accumulated. The universe at this point is in a state of dense and hot gas, that is, plasma. Its components are no longer atoms, not ions, but those very tiny particles, quarks. This is called quark-gluon plasma. At this point in the universe, all the necessary ingredients, specific particles, characteristic forces for the creation of stars and planets are collected. The solution of quark-gluon plasma, in which quarks move in an expanding primordial soup, becomes the seed from which all the building blocks of our universe are formed. This era is known as the quark era. The universe was filled with an amazing array of elementary particles. However, the temperature and energy were still too high for any of these fundamental particles to interact significantly with each other. But time passes, the universe continues to expand, and the temperature drops. The electromagnetic, circular, strong, and weak interactions finally form in their current state. The quarks from the previous quark era slow down their frantic movements and begin to interact with each other for the first time, combining to form the hadrons, protons, and neutrons that make up the nucleus. Let's look at a proton. It consists of 2 up quarks and 1 down quark. We see from the table that both up quarks have a positive charge, but the laws of physics dictate that like charges should repel each other. We are familiar with this even from everyday experience. The closer the like charges are, the stronger they repel each other. This is an example of electromagnetic interaction. To overcome it, you need to put in a lot of effort. In everyday life, we encounter similar processes with the help of a magnet. I think everyone has tried to connect like charged sides. To connect them, you need to put in a lot of effort with your hands. And in order for elementary particles not to repel each other, the force of strong interaction is required. Gluons, the carriers of this strong interaction, hold quarks together and a drone is formed. At this point, the quark-gluon plasma actually cools down, and the quarks are still beginning to group together, forming the first atoms. This first happens in the first second of the existence of the universe. It is not that small. The cosmos at this stage is the size of several solar systems. The era of incredible spontaneous births and exchanges of particles is finally coming to an end. Those particles that now have mass already have it thanks to polyhexes. The 4 fundamental forces that govern our lives today, the strong interaction, electromagnetism, the weak interaction, and gravity, are in full force. The wild and elemental space is gradually turning into a decent system. Earlier, we asked ourselves what everything around the modern universe consists of. We found the answer together with you. Everything around consists of elementary particles. We analyzed the standard model, quarks, leptons, bosons. But the question arises, how did 17 simple elements form the more than 100 million substances that scientists now know about? They are all made up of just 117 chemical elements from the Mendeleev table, which you have probably all seen. The next question arises, how did these chemical elements come to be? All chemical elements are made up of atoms, and they are structured in the same way. Their structure consists of a nucleus and electrons orbiting it. The nucleus consists of positively charged protons and neutrons, which have no charge. The simplest nucleus is the nucleus of a hydrogen atom, which has only 1 proton. The next simplest element is helium. Its nucleus has 2 protons. After all, the number of protons is the number of elements in the Mendeleev table. But what about neutrons? Most hydrogen nuclei do not have neutrons at all. They simply represent 1 proton. This is the simplest type of hydrogen against. But there is also hydrogen in the nucleus of which the proton is accompanied by a neutron. This is deuterium. And even 2 neutrons is already a third. Different subtypes of the same chemical element, but with different properties, are isotopes. All elements have them. In the following story, we will only need isotopes of hydrogen and helium. Helium has 2 stable, non-radioactive isotopes. This is helium, 4 in the rarer helium, 3. These numbers indicate the total number of protons and neutrons in the nucleus. Let me remind you that today there are 118 elements in the Mendeleev tables. There are at least 90 elements on Earth. 98% of its mass falls on just 6: oxygen, silicon, aluminum, magnesium, calcium, and iron. This is, so to speak, the geochemical 6. There is another 6, the biochemical 6. It includes the elements that predominate in the composition of a living cell. These are hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. Our planet is a storehouse of chemical diversity compared to space. The universe as a whole is very boring. 91% of atomic nuclei are the simplest element, hydrogen. Almost 9% are the second simplest element, helium. And less than 1% are all the other elements. That is, most chemical elements were formed in the first 10 seconds of the existence of space. At this point, the time comes for the creation of more complex structures from elementary particles. The universe becomes colder. The temperature becomes suitable for the formation of deuterium nuclei, which I mentioned earlier. It consists of a proton and a neutron, as well as an electron, which is in a conditional orbit of the nucleus. All this forms an elementary atom. But in the current cosmic soup, the temperature was high enough that the average energy per particle was greater than the binding energy of that atom. So any deuterium that formed was immediately destroyed. This situation is known as the deuterium bottleneck. Until it is overcome, the atomic formation simply cannot progress beyond the fusion of one proton and one neutron. But then the universe cools. The temperature allows the deuterium to become more stable. It is now able to fuse with individual protons under the force of intense compression. As a result, an entirely new stable element appeared for the first time, helium-3. Helium-3 adds an extra neutron, forming helium-4. Helium-4 nuclei are the most stable of all existing atomic nuclei. They are the most difficult to split. These processes lead to a significant burst of element formation. Almost all of today's helium was formed during this period. Even the stars, tireless generators of helium, produced very little compared to the primordial formation of nuclei. Many primordial elements were formed, but the processes during this period did not lead to chemical diversity. The concentration of helium was too small for it to become the material for the creation of new elements. How, for example, does this happen in stars? It is true that lithium, beryllium, and boron were formed from helium, but in very small quantities. Moreover, these nuclei are destroyed in thermonuclear reactions as easily as they are created. Eventually, after about 20 minutes of furious cosmic nucleosynthesis, the nuclear furnace calms down and stops. It is still very hot by human standards, but it is simply too cold for new nuclei to form. At this point, there are 12 hydrogen nuclei for every helium nucleus, and nuclear fusion itself has ceased. For every particle of matter, there are many photons, particles of light that have been actively formed through chemical processes. The presence of these ingredients then provides the basis for the formation of everything else. At this point, the universe is matter, a hot, dense plasma of atomic nuclei, electrons, and photons. The act of creating elements ceased after only 20 minutes of the universe's existence, as space expanded and cooled. The entire cosmos was still extremely dense, and the temperature was still too high for the electrons to slow down enough to be captured by the newly formed nuclei of the elements. The universe, which existed as a hot plasma, still had more energy than matter. It would take tens of thousands of years before further cooling would cause further changes. It was only when the ambient temperature dropped to about 4,000 Kelvin that particles were able to combine with each other to form a full atom. The Yadrigals were the first to collect a full set of electrons, and the rest of the matter in the universe at that time was still mostly made up of individual protons. They began to slow down and seek out oppositely charged particles to become electrically neutral. But capturing free electrons was more difficult than borrowing them from helium nuclei. And although the electromagnetic force resisted, helium still transferred electrons through repeated collisions with hydrogen nuclei. This formed the first chemical bonds and the simplest compound of helium and hydrogen. It was called the helium hydride ion. It is the very first molecule in the universe. This molecule is extremely short-lived, but it paved the way for the creation of other molecules. And it was this molecule that laid the foundation for cosmic chemistry. At this point, about 100,000 years had passed since the birth of the universe. For the first few 100,000 years, the universe was completely invisible, despite being full of light. The photons in the plasma were, as it were, trapped in a cage. Since the particles were very tightly packed, it was difficult for the photons to travel long distances without colliding with one of the particles. The path of the photons was like moving through a maze, which led to the scattering of light. As a result, the universe was opaque to light all this time. The photons could not penetrate very far into space, and they were, so to speak, trapped in this seething crowd of particles. When nuclei formed, the electromagnetic force captured the negatively charged electrons. The electromagnetic force is about 100 times weaker than the strong force that holds the particles of the nucleus together. It took 380,000 years of cosmic expansion for the temperature to drop to 3,000 Kelvin. And the drop in temperature caused the electrons to attach themselves and create stable atoms. Some electrons now bind tightly to positively charged ions and open up space for light particles. They begin their journey through space. They are the first light to actually penetrate space. What was previously invisible becomes visible. The wandering photons do not interact with hydrogen atoms, but instead begin to move in straight lines. The universe becomes more transparent, and at this time the last photons enter space. This happened 380,000 years after the Big Bang. The photons begin their journey through the expanding space. The universe is no longer invisible. The frantic energy of light formation in gas flow. It will take millions of years before a new process, nuclear fusion, begins to concentrate light energy again. The dark ages of the universe have arrived. During this time, space is characterized by almost complete darkness. But if nothing is visible, this does not mean that nothing is happening. Dark matter begins to shape the future of the universe. What is dark matter? In fact, we know almost nothing. We only guess. Dark matter does not emit or absorb light and does not participate in electromagnetic interactions. This is how it differs from ordinary matter. Scientists do not yet know what dark matter consists of. However, they are sure that its main component cannot be any of the known elementary particles. The main thing is that dark matter participates in gravitational interactions, including in the dark age of our universe. Dark matter halos formed. They collected atoms along thin threads that grew with space. These gas clusters will become breeding grounds for the first stars and galaxies. The density of the thread will increase by 24 times in about 10 million years. The universe at this time in its history was dark and full of relatively hot hydrogen gas. The universe is expanding. After 12 million years, neutral hydrogen begins to combine into molecules. Hydrogen and helium combine into gravitationally bound clouds of gas. The stars that form the clouds then quickly condense to the density of stars. The first stars are formed. They were hot and short-lived, but also very massive. They weighed between 100 and 400 times the mass of our sun. They glowed incredibly brightly. They burned with such intensity that their energy production could only be sustained for 2 to 3 million years. But we owe our existence to these early stars. They burned their fuel at an incredible rate and made the development of the universe possible. Thanks to this, the universe begins to enrich itself with more complex elements, such as oxygen, nitrogen, carbon, iron, which we are also made of. At the end of their lives, just a few million years after their birth, these stars burn brightly, rapidly burning hydrogen, and their death, as unusual as their birth, creates new chemical elements. Depending on their size, They die in many unusual ways. The brightest lights during this period were caused by the death of the first stars. At the end of their lives, some stars undergo core collapse. When a massive star collapses, it produces a shock wave that can trigger thermonuclear reactions in the star's outer shell. These fusion reactions create new atomic nuclei in a process called nucleosynthesis. This process is called a supernova. They are thought to be one of the original sources of elements heavier than iron in the universe. After a supernova, all that remains is a dense core and hot gas called a nebula. The first stars in the universe were the brightest, most pinpoint sources of light, and they marked the end of the Dark Ages. They transformed the light elements created in the Big Bang into the more complex ones that formed the modern universe. The first stars left behind monstrous black holes with powerful gravitational poles. They may have formed what would later be found at the center of every large galaxy, a supermassive black hole. They are millions or billions of times more massive than our sun. Clusters and superclusters of galaxies form. A new era begins. Eros, the universe, is the largest structure of all our existence. We are just a consequence of its existence. The universe is the foundation of the world, the source of all that exists. It is larger than we can imagine. The universe exists independently of our perception, our desires, or our ideas. It all exists for us. Despite the importance of the universe, there is a theory of parallel universes and many other dimensions. For example, the theory of the multiverse. According to this theory, there are many parallel universes. Each of them contains its own laws of physics and its own unimaginable structure. This theory suggests that all possible scenarios of an event can happen simultaneously in different worlds, which leads to an infinite number of possible realities. And string theory, for example, suggests that our universe has more than 4 dimensions. In addition to the 3 spatial dimensions, length, width, height, and one-time dimension, there are many hidden dimensions that were formed at the very beginning of the universe. And yet, the universe we are talking about is the highest step in the hierarchy of our reality. Perhaps there is nothing higher, or perhaps we are simply unable to understand the highest laws of nature. Perhaps the universe itself is part of an even larger structure. But for now, we are too small to know the answer. We are a tiny part of our universe. We are on a paper boat in the middle of the ocean, and our goal as humanity is to understand this ocean. Humanity is on the threshold of future cosmic discoveries. The future generation, I am sure, will find answers to many of our questions. Perhaps not to test our theories, but to expand our understanding of the world. But for now, it is important for us that the history of the universe does not break. It is slowly, very slowly evolving before our eyes. And in the meantime, we are witnessing a new era, the era of matter. Looking at the night sky, it seems that the stars and galaxies are located more or less chaotically. But this is not quite true. Despite the chaos, the universe is not a disorderly pile of objects. The universe has a structure consisting of massive filaments and galaxies, separated by giant voids. This structure is called the cosmic web. It is filled with galaxies and superclusters. The largest structures in the universe are elongated filaments, galactic filaments, and thin sheets of matter. These filaments extend for hundreds of millions of light years, joining at the ends and surrounding vast, seemingly empty regions called voids. These are regions of space where there are virtually no galaxies or other large objects. These are regions of space and time where the gravitational influence is less significant than in the surrounding regions. The most common components found in voids are proto-glacial clouds. They are made up of the dust and gas that form galaxies. It's all about the wall and the cluster. To form the cosmic web, the high and low density regions, are connected and complementary. But why is there more structure in some places and less in others? The reason lies in the time of the initial inflation, when the universe expanded from a body smaller than an atom to many times larger. We've talked about this before. Gravity is the property of material objects that attract each other. For billions of years, gravity has been fighting the expansion process. When some areas of the early universe became a little denser, this excess density attracted more matter to itself because of gravity, making it even more massive and increasing its gravitational pull. Nebulae, dust, and gas-condensed stars joined them into galaxies and so on. The reason for the formation of such large structures is ultimately due to gravity. Then another question arises: where did the first condensations come from? In the earliest universe, there were tiny fluctuations that, through the expansion of space and the contraction of gravity, gave rise to the structures we see today. At the beginning of history, the observable universe was small, hot, and dense. These were tiny quantum fluctuations with very small differences in space. Then rapid inflation expanded this universe to enormous scales. Inflation inflated the quantum noise into current density differences, giving gravity everything it needed to work its magnetic magic. Mass of matter coalesced into stars, galaxies, superclusters, and filaments. Incomprehensible tiny quantum fluctuations gave rise to vast intergalactic filaments many millions of light years long. You and I live in one of these filaments. Our filament is called the Cetus Piscium supercluster complex, which contains the Laniakea supercluster of galaxies. Laniakea has several members. The first of these is a local supercluster of galaxies, one of which is our Milky Way. The next element is the Hydra Centaurus supercluster. The Pavoni supercluster follows, and the last element is the Southern supercluster. The entire Laniakea region can be imagined as a valley surrounded by mountains, the tops of which are the supercluster, from which rivers or galaxies flow down to the lowest point of the valley. The lowest point of this valley is the Great Attractor. Judging by the effect that the attractor has on the galaxy we observe, it has a mass of tens of thousands of masses in the Milky Way. For this reason, our galaxy, along with its neighbors, is rushing towards it under the influence of gravity, and together they form a huge stream of galaxies. This is the Great Attractor, the center of attraction for everything at a huge distance. But beyond it lies an even more powerful point of attraction. This is the Shelly supercluster, which may weigh 4 times more than the Great Attractor. It is 650 million light years away. It is currently the most powerful point of attraction in the observable part of the universe. The Shelly supercluster is attracting the Great Attractor along with Laniakea and the Virgo supercluster, which we are located next to. To put it in perspective, the Virgo supercluster consists of 100 groups of galaxy clusters. One of the clusters we are interested in is the local group, which is also part of our Milky Way. The local group of galaxies consists of more than 50 objects, each of which is a galaxy of one size or another. These galaxies are gravitationally bound to each other. They all rotate in space around a common center, the MAZ. Observations of the galaxies that are part of the local group have shown that they have a certain structure. That is, they are not located randomly, but for the most part meaningfully. Almost all the galaxies of the local group are located along the lines that can be roughly drawn between the Milky Way and the Andromeda Nebula. Smaller galaxies are mainly concentrated around 3 large galaxies: the Milky Way, Andromeda, and Triangulum. The local group is dominated by 2 galaxies, our Milky Way galaxy and the Andromeda galaxy. It is about 2.5 million light years away from us. Galaxies that are in close proximity to each other can, under favorable conditions, interact in colossal mergers. Their gravitational attraction to each other leads to close interactions, or actual mergers. Galaxies have changed and will change over time precisely because they are in a gravitational dance with each other. When they interact, they can tear each other apart. In some cases, collisions end with one galaxy swallowing another, including the Milky Way swallowing other dwarf galaxies. As the largest member of the local group of galaxies, Andromeda also interacts with other galaxies. For better or worse, its path crosses our Milky Way, and in 3 to 4 billion years, Andromeda will merge with our galaxy into a dwarf. Although it is difficult to predict the motion of such huge objects, recent studies suggest that a collision is inevitable. How will this happen? When the galaxies get close enough, their cores will begin to rotate around each other at a tremendous speed. During this dance, the stellar disks will fly apart due to gravitational interactions. They will fly apart like splashes of water. The cores will rotate faster and faster until they merge into a new massive center. We are approaching a conversation about a very important object in our universe. If you look at a galaxy from the point of view of this SS, it is a tiny part of the universe. And for our ordinary level, a galaxy is an endless sea. There is an incredible variety of types and kinds of galaxies in the universe, and ours is only one of billions. Of course, many of them are similar to our spiral Milky Way, and many are very different. There are small, irregular, and amorphous galaxies. There are galaxies that merge and interact as a result of this process, acquiring distorted shapes. Finally, there are massive galaxies without a clearly defined core. At the same time, they are a giant whirlpool of stars. Galaxies can be completely different. At the center of most large galaxies is a supermassive black hole. It is believed that the birth of a black hole and the birth of a galaxy are directly related. According to one version, a supermassive black hole appeared as a result of the merger of many stellar mass black holes left over from the supernovas of the first stars. According to another version, supermassive black holes were formed as a result of the collapse of a giant gas cloud. In the center are expanding galaxies. From the first galaxies, even larger galaxies formed, which over time turn into giant galaxies much larger than ours. When the universe was younger, smaller, and galaxies were closer to each other, they collided much more often. When smaller galaxies merge to form larger ones, it is called a hierarchical scenario. This is how the Milky Way was formed. It is a spiral galaxy, which is a large disk with stars and gas arranged in spiral arms toward the center. At the center of the disk is a bulge containing a supermassive black hole. The disk is surrounded by a roughly spherical cloud of stars called a halo. At the center is the bulge. The bulge and halo are the oldest parts of the galaxy. They must have formed 13 billion years ago from the merger of dwarf galaxies, compact and dense, like larger versions of the globular star clusters we see today. The spiral disk is 10 billion years younger and is thought to have grown by capturing smaller galaxies. What is a galaxy? Basically, it is not much different from higher-order objects. A galaxy is a gravitationally bound system of stars, star clusters, interstellar gas and dust, dark matter, and planets. In simple terms, it is a cluster of cosmic objects orbiting a common center of mass. After the Big Bang, not only did expansion begin, but cooling also began. The gas was distributed evenly, but there were still irregularities that allowed the gas to begin to coalesce and accumulate into thick clouds. As they heated up, they began nuclear fusion, forming stars, which later also began to approach gravity. They gather into groups that we call galaxies. The galactic center is surrounded by several clusters of young stars, including some of the most massive known. All of them are shrouded in dense clouds of superheated gas. The turbulence in this region is apparently created by the gravity of a monstrous black hole. This monster has a mass of about 4 million suns. The black hole swallowed nearby objects and cleared the field around itself, leaving only stars whose orbits are at a safe distance from it. Next, we see the bright central cluster of galaxies. It consists mainly of old stars. They move around the center of the galaxy in elongated elliptical orbits. This is called the bulge, which was mentioned earlier. The formation of the bulge begins at the very birth of the galaxy, so it consists of the most ancient stars, neutron stars, and the remnants of exploded supernovas. This region is the most concentrated and bright part of any galaxy. The Milky Way is a bar of a spiral galaxy. This is the name of the bright band of stars in the center of the galaxy. In the center of this bar is the core of the galaxy, which we just talked about, and to its edges are adjoined by spiral arms. The gravitational path has at least 5 spiral arms: Cygnus, Orion, Perseus, Sagittarius, and Centaurus. Our solar system is located in the Orion arm. It is connected to 2 other larger arms, the inner Sagittarius arm and the outer Perseus arm. The spiral arms have 2 main components: a spiral pattern formed by older stellar populations and regions of dense interstellar gas, as well as younger objects. Stars, gas, and dust move in elliptical orbits around the center of the galaxy, moving in and out of these spiral arms. As they slow down and collide with each other, the denser regions begin to collapse and become star-forming nebulae. All of the above applies to the visible part of the galaxy, the disk. We usually see it in photographs. Around the disk is the hollow galaxy, an invisible spherical region surrounding the galaxy. This region is mostly made up of dark matter and contains few objects. The hollow galaxy can be said to be a transition zone between the rest of the universe and our galaxy. The most amazing active galaxies, quasars, are usually billions of light years from Earth. They are usually young galaxies with many stars and a lot of gas and dust, which are blown out by a still-growing central black hole. The matter falling on it is heated to millions of degrees and emits a wide range of frequencies, from radio waves to hard X-rays. The light from the active nucleus overlaps the light of its galaxy, and in all but the most powerful telescopes, these objects look like stars, hence the name quasar or quasi-stellar radio source. In general, a galaxy is one of the most beautiful and majestic creations in the universe. Millions of stars and systems around them, black holes, including supermassive ones at the center. Galaxies of all types are titanic and amazing objects. Stars are the fundamental element of our universe. Without them, there would be no life on Earth, because they are the sources of light and heat. Stars are not just bright dots in the sky. They are giant balls of hot gas that are many light years away from us. Every night we look at the sky and see thousands and thousands of stars. In reality, there are many more billions, trillions. Each star has its own history, its own destiny. Some of them have just been born, while others are already on the verge of extinction. Stars are born as a result of the collapse of huge clouds of interstellar gas and dust, which are dominated by hydrogen. In clouds called nebulae, clots of enormous density are formed. Interstellar matter is distributed very unevenly in the galaxy. There are places that are practically empty, and they are filled with very rarefied and hot gas. And there are so-called interstellar molecular clouds. In them, the gas density is quite high by carbon standards, and this gas is very cold. It is in molecular clouds that very dense clots are located, nuclei, which are future stars, a kind of embryonic stars. Molecular clouds are formed as a result of the collision of turbulent flows of interstellar gas. A compaction is formed in the place where this happened. The molecular cloud continues to fall on itself and disintegrate into separate fragments. They become gravitationally unstable. As a result, the compression that begins with a whole molecular cloud gradually moves to small scales and leads to the formation of stars in individual cores. The initial element of this star formation process is the so-called prestellar core. When a specific core is called prestellar, it is emphasized that there is no stellar object inside this core yet. We only have a clot, a very cold gas clot, which is compressed under the action of its own gravity. During compression, the gas heats up, but up to a certain point, the clot is transparent enough, and the excess heat that is released during compression escapes into the environment in the form of radiation. Therefore, the temperature of the clot does not increase. This is not good for the formation of a star, since in order for it to ignite, the matter must be sealed to a temperature of millions of degrees. Only at this temperature do thermonuclear reactions ignite, which make a star with viscous matter. While the clot is transparent, it contracts at a very low temperature. Over time, the dense clot increases in size and becomes less transparent. At some point, the radiation is trapped inside this clot. It can no longer escape from it. The compression continues. The clot continues to heat up, and it can no longer give off this energy. Cooling down, and the temperature in its central part begins to gradually increase. At the moment when it reaches several million degrees, thermonuclear reactions begin. First, deuterium burns as a more flammable element, and then hydrogen ignites. It is at this moment that the protostellar clot becomes a star. But how do thermonuclear reactions occur in a star? What happens inside? Let me remind you that the bodies around us are made up of molecules. Molecules are made up of atoms, and almost all the mass of atoms is concentrated in atomic nuclei. Atomic nuclei, in turn, consist of protons and neutrons. Protons and neutrons, in turn, consist of quarks. Each of them contains its own matrices. The quarks inside a hadron are in the field of strong nuclear interaction, one of the fundamental forces. A body placed in a certain field receives a certain amount of energy as a result. For example, a stone raised above the ground begins to have potential energy. It is proportional to its mass, acceleration under the force of gravity and height. A charged body placed in an electric field will also have potential energy. The quarks inside a proton and neutron have a certain amount of energy, which is due to their participation in strong interactions with each other. But since this energy is kind of hidden inside the proton or neutron, we do not see it from the outside. 9/10 of the mass of protons and neutrons is actually conserved energy, and this energy can be released, which is what happens as a result of processes that we call nuclear reactions. It is also worth paying attention to one oddity. The mass of the nucleus as a whole, consisting of protons and neutrons, differs from the sum of the masses of the protons and neutrons separately. As a result of the fusion of protons and neutrons of the nucleus, part of their mass, due to the binding energy of their quarks, turns out to be excess and is released. If we assemble more complex nuclei not from individual protons and neutrons, but from other, simpler nuclei, as happens in practice, then we will also notice that the resulting nucleus will have a smaller mass than the sum of the masses of the nuclei from which we composed it. This tendency is characteristic of all light atoms. The more protons and neutrons in an atom, the smaller the mass per proton and neutron. This means that the fusion of simpler, more complex atoms will release energy. This process is called nuclear fusion. Recall that in addition to the strong interaction, the electromagnetic force acts in the universe. The nuclei of atoms do have a positive charge, as they consist of neutral neutrons and positively charged protons. As a result, electrostatic repulsive forces prevent them from merging. Electric forces create a potential barrier between atoms, which is called the Coulomb barrier. In order for the atoms to overcome this barrier and collide, starting the process of nuclear fusion. Firstly, they must be close to each other, and secondly, have sufficient speed. In the language of the parameters of matter, this means that for thermonuclear fusion to begin, the substance must be under high pressure and have a high temperature. We are talking about millions and even tens of millions of degrees. In stars, the main type of thermonuclear reaction is the multi-stage conversion of hydrogen into helium. Roughly speaking, 4 hydrogen atoms sequentially merge into 1 helium atom. But not all protons are converted, but only those in the center and those that were lucky enough to collide with each other. During the rest of their sleep, it is too cold for helium to form. So the protons line up around the center of the star and patiently wait for their turn. The average lifespan of stars depends heavily on their mass and can range from a few 100 billion years for the quietest and lightest stars, up to a few million years for the incredibly bright ones, which are many times more massive than the sleeping ones. However, for most of their existence, all stars consume energy and emit light due to thermonuclear reactions occurring in their cores. This process marks a long period of stability in the characteristics of the star, life on the main sequence. All such stars obey the relationship between the total energy of the radiation and the color and temperature of the surface. The higher the luminosity, the hotter the surface and the deeper the light. Mass measurements have shown that the properties of main sequence stars are also related to their mass. Light stars are usually cool, red, and very dim, while heavy stars are hot, blue, and very bright. These patterns are due to how gravitational compression and the conditions inside the core, determined by the star's mass, affect the rate of thermonuclear reactions. Stars with a mass less than half that of the Sun are very different from their counterparts. In the cores of such stars, hydrogen burns much more slowly, so they are very dim and their surfaces are cooler and redder. Red dwarfs are very common. In all galaxies, there are significantly more of them than bright stars. Proxima Centauri, the closest star outside the solar system to us, is a red dwarf. Although it is only 4.5 light years away, it can only be seen with a very powerful telescope. Unlike other stars, red dwarfs are able to support in vitro reactions due to their internal structure due to their outer layers. This means that although red dwarfs contain less matter than other stars, they can theoretically live for hundreds of billions of years. Conventional thermonuclear fusion in its most common form, that is, burning hydrogen, occurs only in stars whose mass is more than 8% of the Sun's. If the star's mass is less, then these are unsuccessful stars, brown dwarfs, which glow faintly as a result of thermonuclear reactions based on deuterium, a scarce isotope of hydrogen. Despite their small energy output, red dwarfs can be surprisingly violent, their twisted layers generating a magnetic field with a complex structure that is much stronger than the magnetic field of our Sun and more massive stars. These fields are capable of generating powerful stars and flares when the stars briefly increase in luminosity. In the cores of massive stars, the temperature and pressure are higher than in the Sun, which accelerates thermonuclear reactions. These stars burn through their fuel quickly and may only last a few million years. Most massive stars have surfaces that are hotter than 20,000 degrees Celsius or more at sunrise. This is why they appear blue. At even larger masses, the pressure and radiation are so great that, despite the increased energy supply, the surface of the star can become cooler. The star swells to such a size that less energy passes through each part of its surface. These supergiants are the brightest stars in the modern universe, and they come in a wide variety of colors. The high pressures and incredibly high temperatures at the center of most massive stars make nuclear fusion reactions more efficient, causing stars with masses much greater than the Sun to shine hundreds of thousands of times brighter. In most of these enormous stars, the pressure and radiation coming from the core becomes so great that they can overcome the force of gravity. This counteracts the powerful stellar wind, causing the star's material to be ejected into interstellar space. Due to the energy calculations, this happens millions of times faster than in stars like the Sun. These are Wolf-Rayet stars, a rare class of massive stars in which the lower layers are ejected into the surrounding space, and the hotter material rises to the surface. Over the course of a few million years, such stars can eject up to half their mass. This battle between internal gravitational forces and external pressure sets an upper limit on the mass of a star, 150 solar masses. Beyond this threshold, any star formed by the fusion of the original cosmic matter will shine so brightly that it will explode before its end. Many of the brightest stars in the path of Melitza are part of binary or multiple systems. This stellar pair or group is formed when two or more centers of mass emerge from emerging nebula and accumulate matter, while remaining in orbit around each other. In rare cases, crowding inside stars in a forming nebula or in dense labular clusters can cause stars to orbit each other or even change partners. Some stars have orbital periods of several thousand years. Other binary systems are so tightly bound that their orbital periods are only a few hours or even days. As a star nears the end of its life, it gradually exhausts the hydrogen in its core, which is needed for nuclear fusion. This causes a series of changes inside the star. The radiation pressure acting toward the center decreases and can no longer withstand the pressure of the upper layers, so they collapse onto the core. The layers heat up and nuclear fusion begins. This may seem surprising to some, but this ignition of the shell causes the star to become significantly brighter. The increased pressure and radiation cause the outer layers of the star to swell. The result is a red giant, a bright star with a much cooler surface than before. In about 5 billion years, our sun will suffer the same fate. As it expands, it will encompass the orbits of Mercury, Venus, and perhaps even Earth. Red giants go through several stages of evolution. Most stars gradually become hot enough at the core for nuclear fusion to begin again. When the core runs out of hydrogen, carbon, nitrogen, and oxygen begin to fuse from helium. Once the core runs out of fuel, helium nuclear burning moves into the shell. As a result, the star is forced to constantly search for delicate internal balances from time to time, exhibiting instabilities that manifest themselves in long periods of pulsation, volume, and brightness. A planetary nebula is the beginning of a short but beautiful final stage in the life of a sun-like star. As the inner shells of a red giant, where thermonuclear reactions occur, expand and approach the surface, the swollen star becomes increasingly unstable and begins to shed its outer layers into the surrounding space. If it were not for the intense radiation from the remnants of the central star, the resulting gas shell would gradually spread and cool, becoming invisible. However, when the inner layers of the star are exposed, its surface temperature rises by tens of thousands of degrees Celsius, and the radiation, most of which is in the ultraviolet range, charges the gas with energy for several thousand years. This is why the glow of planetary nebulae is similar to the glow of emission nebulae. Where stars are born, the shape of planetary nebulae is very diverse, and the core turns into a neutron star. The cores of the most massive stars are compressed to the point of infinite density. This is how a black hole is formed. Supernova remnants play a key role in the evolution of other stars and solar systems. Expanding and mixing with the surrounding non-stellar matter, they add heavier elements to it, accelerating the nuclear fusion of the next generation of stars. In addition, they are greedy for the formation of rocky planets of Mother Earth. Shock waves, moving through the surrounding nebula and compressing it, can themselves cause the birth of new stars. When the core of a monster star collapses during a supernova explosion, one of the most incredible objects in the universe is formed, a neutron star. A substance whose mass is 1.5 times greater than the mass of the Sun is compressed to a sphere with a diameter of about 20 kilometers. The density is so high that a pinhead made of this material would move like a loaded supertanker. Many newly formed neutron stars typically spin very quickly, at hundreds of revolutions per second. Some are wrapped in such a strong magnetic field that most of the radiation emitted by their surface comes in narrow beams directed away from the magnetic poles. Since the axis of rotation of the star rarely perfectly coincides with the direction of these magnetic field lines, pulsars are formed, objects that emit rays like a celestial poppy. Anyone in the path of these rays sees a rapid pulsation. If it were not for this flickering, tiny neutron stars, despite their powerful radiation, would be almost invisible. Most often, a supernova explosion leads to the formation of a neutron star. However, sometimes even more incredible strange objects are formed, black holes. Black holes are formed as a result of the collapse of a large stellar core. All the mass of the core is concentrated in a circular region of space, and the density of matter in it tends to infinity. This object, to which the equations of general relativity do not apply, is called a singularity. It is separated from the rest of the universe by an impenetrable object called the event horizon. The event horizon marks the boundaries of space where gravity is so strong that not even light can escape. Although the black hole itself is invisible, its presence is detected by the gravitational effect it has on other objects. A black hole can make itself known if it attracts matter that is too close to it. As it spirals toward the event horizon, matter is torn apart and heated to very high temperatures by the rapidly increasing gravitational field. A fading burst of radiation in X-rays and other geographic ranges marks the absorption of matter and its addition to the singularity. The universe has 4 dimensions, 3 spatial and 1 temporal. We can think of space-time as a huge elastic sheet that bends and stretches as planets, stars, and galaxies appear on its surface. The greater the gravitational mass of an object, the more it bends the space around it. Most people think of space as a void in which everything happens. It's like a big empty warehouse or a theater stage where the events of the universe unfold. In this sense, space is the absence of things. It's a void waiting to be filled. For example, I saved room for dessert, found a great parking spot, a place with nothing. But if you follow this idea, space can exist on its own without being filled with matter. For example, if you imagine that there's a finite amount of matter in the universe, you can imagine that you've flown so far that you've reached a point beyond which there is no matter at all. If you follow this idea, space can exist on its own without being filled with matter. For example, if you imagine that there's a finite amount of matter in the universe, you can imagine that you have traveled so far that you have reached a point beyond which there is no matter at all, and all the matter is left behind. In front of you lies pure and empty space, and beyond that, space can stretch to infinity. In this view, space is an infinite void. But physics has another version. Instead of being something like an empty room, space is more like a huge piece of wood in a vein. Normally, objects can move through a vein without any problem, just as we can move through a room filled with air without noticing the air. But under certain conditions, the vein can bend, changing the way objects move through it. It can also flex and undulate, changing the shape of things inside it. A vein would not be a perfect analogy for the nature of space, but it can help you imagine that the space you are in now is not necessarily fixed and abstract. You are in a certain environment, and that environment can stretch or shake or distort in ways you can't even feel. Matter dictates how space should curve, and curved space dictates how matter should move. The path of light changes. Where space-time is curved, the path of that light is curved. Gravity can also affect time. In the gravitational field of a black hole, you wouldn't notice that a clock is ticking slower, but an outside observer would. In an environment with less gravity, you would see as if you were in slow motion. Now imagine that we could put an object so big that it would press so hard on a plane that nothing would come out of the hole. A black hole is such a region of space. It has no surface. You can't knock on it. You can't walk on it. There is only a horizon, the boundary separating the depths of a black hole from the rest of the world. Such a boundary, a signal moving at the speed of light, is completely contained by the flow and cannot go to infinity in space. There are several theories about how black holes are formed and appear, the most famous of which is the formation as a result of the gravitational collapse of a star with a large mass. We discussed this with you earlier. The second scenario describes the birth of a black hole in the form of compression of protolactic gas, which is at the stage of transformation into a galaxy. In the case of insufficient internal pressure to compensate for the same gravitational forces, a black hole can appear. Black holes are mysterious folds of time and space. They are the most mysterious objects in the universe. Their essence and nature remain unknown to us in the full world. Their true capabilities remain beyond our understanding. What will happen to a black hole in many millions of years? We do not know the answer to this question. Perhaps they will exist forever, absorbing everything around them. Or perhaps they will disappear, disintegrating into tiny particles. Perhaps each of these holes is the embryo of the universe. They attract our attention and imagination. They make us think about the nature of the universe. But so far they do not give exact answers. For you and me now, for this Ezek, the key thing is that black holes are one of the options for the end of a star's life. One of such stars is our sun. It is assumed that the sun cannot turn into a black hole due to its small scale. Perhaps this is even for the best. Now this star is cosmic death for us. This is our native harbor. It is good that it will not turn into an all-consuming monster. And I suggest moving on to studying our native, the solar system. The solar system arose 9 billion years after the birth of the universe, when it had accumulated a sufficient number of various chemical elements. The solar system was formed far from the center of our galaxy, from the center of the Milky Way. It is located in the zone that is considered the most favorable for the origin of life. The origin of the solar system is most likely associated with a supernova explosion that struck our gas cloud and started the process of evolution of the system. 5 billion years ago, our future home was on the outskirts of the galaxy, halfway from the center of the Milky Way. We are in one of the arms among millions of stars. In this modest corner, there was little to be found except a giant cloud of interstellar gas and icy dust. In this modest corner, there was little to be found except a giant cloud that had sunk into a cosmic cancer for many light years. 9/10 of this cloud were hydrogen atoms, and the other 9/10 were helium atoms. The remaining 1% consisted of small organic molecules and microscopic particles of mineral matter. Such a gas and dust cloud can exist in space for many millions of years until some impulse, for example, a shock wave from the collapse of a nearby star, does not start the process of forming a new star system in it. It was this trigger that began the formation of our solar system 4.5 billion years ago. Very slowly, over 1 million years, the swirl of gas and dust was pulled inward toward the center. The giant cloud spun faster and faster as gravity pulled its lighter edges toward the center. As it compressed and sped up, the cloud gradually became denser and stretched into a disk shape, with a new celestial body growing in the center. Thus, our sun was born. This central sphere, having absorbed almost all the hydrogen, grew larger and larger until it had absorbed 99% of the cloud's entire mass. As it grew, the pressure and temperature inside the sphere rose to the point of nuclear fusion, and the sun ignited. The sun, which makes up the lion's share of the total mass of the solar system, dominates it. The sun itself is not particularly massive in our system. Our medium-mass star is in a winning position, not too big, with a short lifespan but not too small, with insufficient thermal radiation energy. Its estimated lifespan is 9 to 10 billion years. This is enough time for life support to develop. Of course, in about 4 to 5 billion years, the hydrogen in the sun's core will run out, and the star will enter the helium burnout stage. After this process, it will swell to an unfriendly red giant. It will become 100 times larger than its current diameter, and for a start, it will destroy poor little Mercury, burn up Venus, and cause great inconvenience to Earth. However, even after 4 to 5 billion years, we still have time until the sun enters its final stage. The solar system has another feature, favorable for life on Earth. Unlike many other planetary systems, ours is formed around a single star. About 2/3 of visible stars are binary, that is, systems in which two stars dance around each other and have a common gravitational center. When such stars formed, hydrogen accumulated in two separate points in space, forming two giant gas balls. But in our system, everything happened differently. In the center of this gas nebula of the field, under the influence of gravity, a star arose, a protosun, surrounded by a wide ring of gas and cosmic dust. In the early stages of the development of the solar system, the planetary disk was divided into two parts with different ratios of rock and gas, water, ice, matter. A natural boundary arose in the protoplanetary disk, dividing the region with solid matter in the inner part, and the region where the bulk of the volatile gases were forced out. In the inner part of the solar system, the terrestrial planets began to form, and in the outer part, the giant planets. Tiny dust particles stick together, forming a large block. Gradually, the dust particles gather into kilometer-sized bodies, which at the last stage of planet formation rake in almost all the primary dust. They eat up most of the dust and gas and begin to conditionally compete with each other. Mutual collisions of such tiny planets can stimulate both their growth and destruction. The orbits of bodies around the star can initially be elliptical, but over time, breaking into gas and mutual collisions turn the orbits into approximately circular ones. At first, the body grows due to a series of random collisions, but the larger the planet Earth becomes, the stronger its gravity becomes, and the more intensely it absorbs its low-mass neighbors. When the mass of planet Earth becomes comparable to the mass of the Moon, their gravity increases so much that they shake the surrounding bodies and deflect them to the side, even before the collision. This is how they limit their growth. This is how the conditional mastodons arise. They fall on planets with comparable masses, competing with each other for the remaining planet Earth. They crash into each other in random collisions, creating a huge amount of heat and friction before eventually sticking together. Once these rocks and bodies reach a certain size, they become so massive that heavier elements and metals begin to sink into the heated core. The core of the planet gradually turns into a planet with a hot inner layered structure. This is how rocky and terrestrial planets are formed: Earth, Venus, Mars, Mercury. And as already mentioned, they are usually closer to the star, where the field disk was much hotter. The gas planets formed a little differently. After their formation, Jupiter and Saturn moved in the inner part of the stem towards the Sun. Under the influence of gravity, a large number of rocky and gas-waterized asteroids rushed there. As a result of resonant connections with the outer asteroid belt, other giant planets, and among themselves, Jupiter and Saturn moved to the outer part of the solar system, where they stabilize in orbits close to their current positions. This stabilization was completed about 4 billion years ago, causing the last major bombardment of the inner solar system with rocky material. At present, our giant gas planets, with their enormous sizes and nearly circular orbits, behave quite well. The largest of them, Jupiter, has a mass 1,000 times smaller than the Sun. This is enough to have a significant impact on neighboring planets. Because of Jupiter's strong gravitational field, the planets sleeping in the asteroid belt never merge into a single planet. However, Jupiter does not have enough mass to initiate nuclear fusion in its own core. How planets are different from stars. Jupiter is mostly made of light hydrogen, but it has a complex chemistry and climate that together produce brightly colored clouds. Despite its enormous size, Jupiter rotates on its axis in less than 10 hours, and as a result, its equator was baked. Because of its rapid rotation, the planet's major weather systems swirl parallel to the equator, creating alternating bands of light and dark clouds. Jupiter's interior resists gravitational compression, releasing large amounts of heat that drive strong winds and storms, including the famous Great Red Spot, an Earth-sized anticyclone that rages for centuries. The distant ring planet Saturn and the even more distant cold planets Uranus and Neptune are much smaller. However, all of these gas giants are large enough to attract smaller debris into their orbits, forming small solar systems within the solar system. As a result, all 4 outer planets have retinues of interesting sounding moons. The most active celestial body in the entire solar system is Jupiter's moon Io, which orbits so close to the gas giant that it takes Io only 41 hours to complete an orbit around Jupiter. Powerful tidal forces constantly affect this moon, awakening about half a dozen volcanoes that throw out giant jets hundreds of kilometers high. This is a unique phenomenon in the solar system. No less interesting are Europa and Ganymede, large satellites the size of Mercury, composed of water and rock in roughly equal proportions. Both of these satellites are heated from within by the influence and army of active tidal forces of Jupiter. Almost their entire surface is covered by an ice-covered ocean. Saturn, the next in line of the outer planets, has more than a dozen moons, not to mention the famous rings, most of which are made of glittering chunks of ice. Most of Saturn's moons are relatively small and are either captured asteroids or fragments of Saturn itself. However, its largest satellite, Titan, is larger than the planet Mercury and is shrouded in a thick layer of orange atmosphere. Branched sidetracks and streams feed cold lakes of liquid hydrocarbons. The thick, colorful, funnel-shaped atmosphere contains a large number of organic molecules. Overall, Titan is worth investigating for signs of life. Saturn itself is the second largest gas giant in the solar system. Its composition is similar to Jupiter. Saturn is less than a third the mass of Jupiter, so it has weaker gravity. This allowed its atmosphere to expand so much that the planets became the same size. At the same time, Saturn's average density was even less than that of water. Its weather system forms the same equatorial parallel bands as Jupiter. But unlike Jupiter's colorful clouds, Saturn's palette is mostly creamy white. In fact, its clouds are probably just as colorful, but their color is muted by a layer of white haze that forms in the cold upper atmosphere. While Saturn has no long-lasting hurricanes to rival the Great Red Spot, superstorms do occur regularly at certain latitudes during certain periods of the long Saturnian year. Saturn has a bright inner ring system formed by highly reflective chunks of ice. Despite their enormous width, the rings are surprisingly thin, forming a plane only a few hundred meters thick. From a distance, the rings appear solid, but only because of the vast number of particles within them. We still don't fully understand the origin of the rings, but it's likely that a once-collapsed icy object played a major role. Collisions of particles within the rings continually renew their material, leaving fresh, bright ice on their surfaces. The most distant gas giants, Uranus and Neptune, have many equally interesting moons. Most of them contain traces of water ice and organic molecules. Uranus is the first of two nearly identical giant ice worlds in the solar system. This is a special class of planets made mostly of chemical ices. This ice contains not only water, but also other easily fusible elements, such as ammonia and methane. Uranus's pale blue-green color is due to the small amount of methane in its atmosphere, which absorbs some colors of sunlight and reflects others. Neptune, like Uranus, is also an ice giant. The two planets are nearly identical in size. They are slightly smaller than 4 Earth diameters in diameter. Closer to our planet, gravitational fields retain their influence. Most of the hydrogen and helium were pushed into the outer giant planets after the Sun ignited, and the inner solar system was a small fraction of the massive matter, mostly composed of rock. Mercury, the smallest of the rocky planets, formed closest to the Sun, a harsh, parched world. It appears empty and lifeless. For billions of years, its cratered surface has remained unchanged under an airless sky. It is believed that during the planet's formation, a collision occurred, causing much of its rocky mantle which surrounded the core to fly off into space. It appears to have first expanded in size over hundreds of millions of years. This caused the outer rocky shell to crack and form blocks of sorts. The next planet in order is Venus. It is similar in size to Earth, but very different in its habitability. This is mainly due to its orbital position, about 50 million kilometers closer to the Sun. It may have once had water, not even a deep ocean, but under the influence of thermal radiation and solar wind, the water on Venus almost boiled away, stripping the planet of all moisture. Shrouded in atmosphere and highly reflective, it looks like a sparkling diamond in the sky, but its beauty belies its devilish nature. In Venus' atmosphere, carbon dioxide turns into toxic carbon, and on the surface, temperatures reach nearly 400 degrees. Add to that clouds of sulfuric acid and incredibly high atmospheric pressure, and it's easy to see why Venus is the most hostile planet in the solar system. Mars is Earth's neighbor and next in line to the inner planets. It's much smaller, only 1/10 the mass of Earth, but in many ways it's similar to our own planet, a day that would last only half an hour for an alien. The surface of Mars is covered in a fine reddish dust, colored by the same chemical that makes rust. The very geography of Mars shows signs of very recent change. Volcanoes on Mars, including Olympus, began to form billions of years ago, but their slopes show traces of lava fields that appeared later, several million years ago. Another notable feature of the Martian landscape is a system of deep faults known as the Mariner-Dolan faults. It is believed that the climate on Mars in the past was much warmer and wetter. In the distant past, the planets migrated within the solar system, The NICE model was the first attempt to explain this process. It suggested that the giant planets Jupiter, Saturn, Uranus, and Neptune were initially located twice as close to the Sun as they are now, and then slowly migrated to the outer part of the system. On their way, they left behind a trail of asteroids and comets, many of which collided with the inner planets. This event is called the Late Heavy Bombardment. Any material that was not used to form planets in the early solar system building site found a home in either the Mars-Jupiter asteroid search, the Kuiper search beyond Neptune, or deep interplanetary space. Given that the inner solar system condensed materials with high melting points, the millions of space debris in the Mars asteroid search are rocky objects made of carbon, silicon, oxygen, and metal. This process may have slowed down, but it did not stop. The water on Earth may have come from a comet or asteroid impact. Our Earth is the third planet from the Sun and the largest rocky planet in the solar system. It is in the habitable zone, where liquid water can remain on the surface without freezing or evaporating. The planet's circular orbit and axial tilt result in consistent seasons, which helps maintain a temperate climate. The existence of the ocean supports the water cycle. As water passes through liquid, solid, and gaseous states, it is absorbed from the seas into the atmosphere, spills onto land, and evaporates again, helping to shape the Earth's landscape. The large core, made of molten iron and nickel, creates a fairly strong magnetic field that envelopes the Earth and protects it from the destructive effects of the solar wind. Heat from the core causes the outer crust to split into dozens of tectonic plates, or loose segments, floating in the mantle at a rate of a few centimeters per year. New crust forms in the cracks. Collisions of tectonic plates form mountains, and where plates melt and sink back, heat is released and chains of volcanoes are fed. This complex environment creates a huge potential for chemical reactions, storing the energy used by all forms of life. Evidence suggests that the first simple organisms appeared more than 4.2 billion years ago. For billions of years, these early bacteria absorbed carbon dioxide from the atmosphere and replaced it with oxygen, which is vital for more complex modern organisms. And at that moment, the evolution of our Earth began.